Welcome to this AHED video. The topic of today's video is the design of a heat recovery heat exchanger. This is the heat transfer problem that we will analyze. As you can see, this is a heat exchanger which receives on the tube side a flow rate of 85,000 kilos per hour of water coming in at 25 degrees and exiting at 45 degrees. On the shell side we will use water at 45,000 kilos per hour at 115 degrees centigrade. And the constraints for this particular problem are that the maximum pressure drop on the tube side and the shell side can be no more than 1 bar. So let's start by opening the AHED program and enter some project details. Let's give a project name here, choose the SI engineering units and set the number of decimals to 3. And let's call our heat transfer calculation simply heat recovery heat exchanger. Now we will define the tube side fluid. Click Tubes Fluid and we select the AHED Fluid database. We search for water in the list, click and add. We enter the product name water and we define the minimum and the maximum temperature for the fluid range, the temperature increment, operating pressure, and then we click calculate. And this way we obtain the fluid properties for the liquid and the gas phase, and we can see them here in a graph. Next we define the shell side fluid, and we will do this in the same way as for the tube side. Click Shell Fluid, select the AHED Fluid database, select water and add, enter the fluid name, and we define the temperature ranges. Start, end, the increment, the inlet pressure, and then we click calculate and we obtain the tables for the liquid phase and the gas phase in exactly the same way. Next up is defining the heat balance. We click heat balance, check the correct heat transfer process for the tube and the shell side, in this case sensible heat. We introduce the tube side flow, inlet temperature and outlet temperature. On the shell side, we mark the outlet temperature as the free parameter to be calculated, and we introduce the shell side flow and inlet temperature. And let's make sure that we have selected counter current flow correctly. We click calculate and the heat balance calculation is performed. The shell side outlet temperature is calculated, as well as the physical properties on the tube and shell side at the inlet and outlet condition. Now let's define the geometry of our heat exchanger. To do so, we click Geometry and we start by defining the dimensions of the shell, in this case a DN200 shell. Then we define the dimensions of the shell side nozzles, in this case DN100 nozzles on both the inlet and the outlet. We set the inner tube to 25 by 1 millimeter and we set the tube pitch. We set the tube length to 6 meters and we define the dimensions of the nozzles on the tube side. Like so. In this case, DN 125 nozzles. By clicking Optimize, we calculate the maximum number of tubes that this shell can hold, 31 tubes. But we can select other kinds of pitches, such as squared. We click Calculate. Now we can hold 24 tubes inside. So for this calculation we will go back to Optimize and work with the maximum number of tubes that we can fit, 31. And let's confirm by Calculate. Now we have to define the baffles. The log window already gave us a warning that baffles were not well defined. So let's click Baffles. And we select the Support Baffle option. Next we define the inlet and outlet pitch for the baffles and we set the number of baffles. We define the baffle cut and we click Calculate. As we can see, we now have 6 baffles evenly spaced over the shell length. Now we will do the heat transfer calculation. We click Overall Calculation and we click Calculate. The heat transfer calculation is now performed. In this part, we see the velocities and the flow types. This section calculates the viscosities and the Reynolds and Prandtl number. In this section, we see the calculation of the wall temperatures, the Nusselt numbers, the side heat transfer coefficients, and the overall heat transfer coefficient. Here we see the calculation of the log mean temperature difference, the area calculation, and the calculation of the excess area. Going to the top, we see the pressure drops that are being calculated on the shell and the tube side, well within the defined constraints. And finally, we see the vibration calculations, which indicates no mistakes. As we can see, the excess area is limited, only 5%, so now we will try to improve the design. To do so, we will redefine the way we have set up the baffles. So let's return to baffles. We will now select the option for full heat transfer baffles. Let's first reduce the baffle cut, 25%. And let's try to fit 28 baffles, with a baffle spacing that is equal or less than the shell diameter which is required for full heat transfer baffles. Like so. Click Calculate, and now we see these 28 baffles evenly spaced over the shell length. Let's go back to overall calculation, click Calculate, and now we see that the heat transfer coefficients on the shell size have greatly improved, and this results in a larger excess area. Let's not forget to check the pressure drops, and we see that they are still within the constraints. Let's now look at the result of our heat transfer calculation in a graphical form. To do so, we click on Graphs, and the following information appears. The graph on the right-hand side shows bulk fluid temperatures and wall temperatures. Below, Nusselt-Reynolds graphs are shown for tube and shell side, where vertical lines indicate the position of the inlet and the outlet. And here we see a small summary of the heat transfer calculation. Finally, let's take a look at how we can report our results. We click on Reports, and a series of reports become available to us. In this example, we will select the full report, which includes all of the above. An Excel file opens, which contains a series of tabs. First, we see the physical property table of the tube side fluid, the same for the shell side fluid, a result of the heat balance calculation, the geometry definition, we see our baffle definition, here is the result of our heat transfer calculation, the graphs are there, and finally a TMA sheet with all parameters. With this we have reached the end. We would like to thank you for your attention, and we hope to see you again in a future video.